Hi and welcome to the second day of Limits Part 2. So we're going to do the examples of trig limits and limits at infinity. Hopefully you have these written down. If you don't, you can pause the video. They were in the video you were supposed to watch for today, but sure, pause the video and write these down. So we'll start with the following examples. Tangent of x, the limit as x approaches pi over 4. Well, we do what we've been doing, and we plug in pi over 4. And because I can evaluate this at 1, I'm done. I got a number, the answer is 1, that's it. For this next one, I plug in 0, and I get sine of 0, which is 0 all over 0, and that indicates to me, ooh, I have to do a little more work. But what do we notice about this one? Hopefully you notice it looks really close to our limit as x approaches 0 of sine x over x, which we know is going to be equal to 1. But the issue is we have this 3x here. So how can I edit? Well, if I had a 3 down here, then these would be the same and we'd be happy. But if I multiply by my denominator by something, I must also multiply my numerator by something. So now I really have the limit as x approaches 3, as x approaches 0 of 3 times sine of 3x over 3x. This part, this limit, as long as the thing in the numerator and the denominator are the same, this is going to be 1. And now I have 1 times 3, which is 3. We got one more, kind of as like a warm-up. The limit as x approaches 0 of 1 minus cosine of 7x all over x. And again, the same thing we're seeing here is it's really close to our limit as x approaches 0. Oh, excuse me, I'm sorry. Of 1 minus cosine of x all over x. And again, if this thing and this thing are the same, this limit will be 0. So how do we do that? Well, we have a 7, so that means we need a 7 down here. And I can do that as long as I multiply the numerator by 7 as well. So I really have the limit as x approaches 0 of 7 times the quantity, 1 minus cosine of 7x all over 7x. This part, because of this rule, goes to 0, and now I have 0 times 7, which is still 0. Pause the video, write down these problems, try them out. I'm going to go through some of these quickly and some of these not so quickly. For this first one, the limit as x approaches 0 of tangent x over x. Well, that's one of our rules. This is just 1. Nothing interesting there. The next one is similar to the last one we've been doing, where we need the same thing in the numerator and the denominator, and we're going to multiply it by 2 over 2, which means my final solution here would be 2. For this next one, we notice it's not exactly one of our rules. So I plug in 0. Sine of 0 is 0. So I have 1 plus 0 in the numerator. Cosine of 0 is actually 1. I get 1 over 1, and my solution is 1. Ooh, and then what about these? These are a little interesting. We're actually going to skip down to this one, because the good thing about our rule is that they are the same for the reciprocal. So if I had tangent of x over x, that would be equal to 1. Because I have x over tangent of x, I also still have 1. This is basically the same as our first problem. It's just the reciprocal, but the reciprocal of 1 is still 1. Last but not least, what about this guy? So I look here and I think, well, this part, we need a 4x in the denominator. So 3 times sine of 4x all over sine of 3x. This first piece needs a 4x down here. Oops. Make that look nice. And if we multiply the denominator by 4x, I'm going to multiply the numerator by 4x. This guy technically needs a 3x up top. Well, look, we have a 3 and an x up top already, so I don't actually have to do anything. So what happens? Well, this along with this and that, this would be 3x over sine of 3x. In this piece, oops, would be 4 times sine of 4x all over 4x. And we still have the limit as x approaches 0. Well, we know this becomes 1, this becomes 1, and then I have 1 times 4 times 1, which leaves me with 4. Next piece of this was limits at infinity. So what happens as our graph gets really, really big or really, really small? And the first thing we talked about was end behavior and leading coefficients. So if x gets really big and my y is getting really big, we say infinity, and remember that therefore does not exist. We say therefore does not exist because infinity is not a number I can actually get to. Then we looked also at our rational function rules, which really were our horizontal asymptote rules. If the numerator has a greater degree than my denominator, oh, sorry, I'm talking about this one right here. Numerator has a greater degree than my denominator. The limit does not exist, and it's either positive or negative infinity. We would consider leading coefficients for this. If they have the same degree, we also consider leading coefficients, and our limit is that. And if our numerator has a lower degree than our denominator, our horizontal asymptote is y equals 0, thus the limit is 0. So we did this example together. Let's start with this one right here. The limit as x approaches infinity of this function g of x. Well, I notice they have the same degree, and so I'm fairly certain I'm just going to take the leading coefficient of the top divided by the leading coefficient of my denominator, and I'm done. But let me show you one way that we could also think about this. I mean, that's the answer, but just to see it in a different way. You wouldn't expect to do this, but what if I took every piece, 2x to the fourth minus x squared plus 8x, and divided by the highest highest degree. So we have something that looks like this. Well, notice these are going to cancel, these are going to cancel. Here we're left with x squared in the denominator, here we're left with x cubed. But the thing that's important is to think as x approaches infinity. As the denominator of a fraction gets bigger and bigger, what does that fraction become? Smaller and smaller. So this approaches 0, this approaches 0, this guy approaches 0, and all we're left with is this 2 and negative 5. If you want to pause the video right now and try these 3 problems, that would be great. Otherwise, I will do them briefly. Limit as x approaches infinity of 3x plus 5 over 6x plus 7. Degree of the numerator and degree of the denominator are the same. That means we use our leading coefficients, 3 over 6, or really 1/2. For this next one, degree of our numerator is less than the degree of our denominator. That means our limit will be 0. Looking at this one, degree of my numerator is greater than the degree of my denominator, which means I don't have a horizontal asymptote. Technically, I have a slant. So I'm going to take that leading term and divide it by the leading term of the denominator. So I'd really have 3/10 x. Well, if I think about that as a line, it's going to be a positive slope. Oh goodness, what is this all over here? A positive slope. And so as x approaches positive infinity here, my y is approaching positive infinity, and we would say therefore does not exist. Ooh, and last but not least, what do we see here? Well, I can tell that the degree of the numerator is 1. And the degree of the denominator is a little more challenging, but if you think about it logically, a square root of something squared, that degree is also really 1. So I can think of it in that way, and that means they have the same degree. And what I would be doing is taking the leading coefficients. But there is a slight difference here, in that this denominator will always be positive, no matter what the numerator is. So this, because of the square root, this will always be a positive number. Well, if I plug in negative infinity here, this numerator would be a -2 over this +1, and so this limit is actually a -2. Again, same with the last one. If you have more questions, we can go through some on Monday, but your assignment for the weekend is the limits at infinity and trig limits worksheets.